Fourth one, what should be the value of lambda such that the function defined below is continuous at x is equal to pi by 2. Given f of x is equal to lambda cos x by pi by 2 minus x, if x not equal to pi by 2 is equal to 1 if x is equal to pi by 2. It is given that function is continuous at x is equal to pi by 2. If it is continuous at x is equal to pi by 2, according to the definition of continuity, I can write that limit extends to pi by 2, f of x must be equal to f of pi by 2. By applying definition of continuity, that limit value at x is equal to pi by 2 is equal to function value. So here, given that function value of f of x at x is equal to pi by 2 is 1, so that is f of pi by 2 value 1. Now we have to find out limit value equal to 1 and find that unknown value lambda. It implies here limit extends to pi by 2 f of x is lambda cos x by pi by 2 minus x. Finding limit value. So if we replace x with pi by 2, here lambda, here cos pi by 2, lambda into cos pi by 2, cos pi by 2 0, by pi by 2 minus pi by 2 0, we get 0 by 0 form. So we have to go for that L'Hopital rule. Limit extends to pi by 2, derivative of lambda cos x is lambda into derivative of cos x is lambda is constant minus sin x, by derivative of pi by 2 minus x is minus 1. So put that lambda outside. Limit extends to pi by 2 sin x, so sin 91, so lambda into 1 will get 1 lambda. So limit value lambda, so function value 1, so it implies lambda must be equal to 1, so that that function f of x is continuous at x is equal to pi by 2. So answer for that fourth question is lambda is equal to 1. Now see that fifth question. Value of a for which the function below is continuous at x is equal to 1. Here f of x is 2x plus ax square, x less than or equal to 1, 4x plus 3 for x greater than 1. Here also it is given that function is continuous at x is equal to 1. So I can say that limit extends to 1, f of x must be equal to f of 1. Limit value is equal to function value. So again here, when that limit value exists here, that limit value exists if and only if left hand limit is equal to right hand limit. That limit value exists if and only if left hand limit is equal to right hand limit. Again here, what is left hand limit here? Limit extends to 1 minus f of x must be equal to limit extends to 1 plus f of x. It implies limit extends to 1 minus means when x less than minus 1, when x less than 1, the corresponding function is 2x plus ax square. When x less than 1, the corresponding function is 2x plus ax square, that is equal to limit extends to 1 plus means when x greater than 1, the corresponding function is 4x plus 3. So these two must be equal. It implies I can write limit extends to 1 minus means here replace x with 1 in that function, will get that left hand limit value. So left hand limit value is will get 2 into 1 plus a into 1 square is a. So 2 plus a is equal to, when x is equal to 1, the right hand limit value is 4 into 1 plus 3, 4 plus 3 is 7. So it implies we'll get a is equal to 7 minus 2, 5. So the unknown value a is 5. So for that fifth question, answer is C. Next question, sixth one. The function f of x is equal to 1 by 1 plus mod x is option A continuous and differentiable, not continuous but differentiable, continuous but not differentiable, not continuous and not differentiable. So here using properties of continuous and differentiable functions, we can eliminate some options. Here we have one property here. Every differentiable function is always continuous. Using properties, I can say that every differential function is always continuous. This is the statement. What is the converse of the statement here? Every continuous function need not be differentiable. Every continuous function need not be differentiable. Need not be differentiable. That is the converse. This is the statement. Statement is always true. Converse need not be true. Every continuous function need not be differentiable. But the contrapositive. Contrapositive is always true. Contrapositive means a function which is not continuous, is not differentiable. Is not differentiable. A function which is not continuous is not differentiable. This is a contrapositive statement. Contrapositive is always true. So now you see the options here. Option A continuous and differentiable. Option B not continuous but differentiable. So a function which is not continuous is always not differentiable. A function which is not continuous is not differentiable always. So that option B is wrong here. I can eliminate option B. A function which is not continuous but differentiable, it can't be differentiable function using that contrapositive statement. So I can eliminate that option B. Now see what about answer here? Answer will be one of option A, C, D. Now to verify that one again, once again we have to go for a concept. What is the given function here? A given function f of x is equal to 1 by 1 plus mod x. 1 by 1 plus mod x. To check the continuity here, see this is the given function is rational function. Whenever a rational function is given, to find points at which given function not continuous, equate denominator to 0. What I am saying, whenever a rational function is given, to find points at which given function not continuous, equate denominator to 0. So for points which are not continuous, for points at which given function not continuous, at which given function not continuous. So it implies mod x is equal to, we got minus 1. See, modulus of x value minus 1. So this is impossible. Modulus of x value is always positive. Mod x value cannot be negative. Therefore, this is impossible. Therefore, so that denominator cannot be 0. Denominator cannot be 0. Therefore, that function is always continuous. Therefore, I can say that f of x is continuous everywhere. Continuous everywhere. No points of discontinuity. No points of discontinuity. So that is regarding continuity. Now, checking differentiability. So how to check differentiability? See here, applying the definition here. What is the definition here? Limit extends to a f of x minus f of a by x minus a. If this limit value exists, then I can say that that function f of x is differentiable at the point x is equal to a. Now again, when this limit exists, I said that limit exists if and only if that left hand derivative is equal to right hand derivative. LHD is equal to RHD, then only limit exists. So again here, what is LHD? Left hand derivative. Here our point here, a is here. See here, we have to go for a critical point. The critical point of the given function is x is 0. So I will check at x is equal to 0. That is the critical point. At remaining points, it is always differentiable as well as continuous. It is enough to check only at critical points. At x is equal to 0, that is the only critical point. So now LHD, left hand derivative at x is equal to 0. Limit x tends to 0 minus f of x minus f of 0 by x minus 0. F of x minus f of 0 by x minus 0. That is equal to limit x tends to 0 minus. So 0 minus nothing but x value less than 0. When x less than 0, mod x value is minus x. So I can write the function here 1 by 1, replacing mod x with minus x minus f of 0. Replacing x with 0, 1 by 1 plus modulus of 0, we get 1 by 1 1 by x. So simplifying this one, we will get limit extends to 0 minus. So here doing LCM, we will get 1 minus 1 plus x by 1 minus x into x plus 1 minus 1 will get cancelled. Again xx will get cancelled. Replacing x with 0, we get 1 by 1 minus 0, that is equal to 1. That is left hand derivative value. Now finding corresponding right hand derivative. Finding corresponding right hand derivative. So the right hand derivative is RHD. RHD is equal to limit x tends to 0 plus. So when x 0 plus f of x minus f of 0 by x minus 0. So limit that is equal to limit x tends to 0 plus nothing but x value greater than 0. When x greater than 0, mod x value is plus x. So I can replace 1 by 1 plus mod x with plus x minus 1 by x. So simplifying this one, limit x tends to 0 plus 1 minus 1 minus x by 1 plus x into x. So plus 1 minus 1 plus x, xx will get cancelled. If we replace x with 0, we will get a minus 1 by 1 plus 0, that is equal to minus 1. So left hand derivative value 1, whereas right hand derivative value minus 1, both are not equal. Left hand derivative not equal to right hand derivative. Therefore, the given function is not differentiable. Given function is not differentiable at x is equal to 0. So given function is continuous at x is equal to 0, but not differentiable at x is equal to 0. So continuous but not differentiable. Continuous but not differentiable. That is the correct option. Next question. Let f be a function defined by f of x, x square for x less than or equal to 1, x square plus bx plus c for x 1 less than x less than or equal to 2, x plus d for x greater than 2. Find the values for the constants a, b, c, d so that f is continuous and differentiable everywhere on the real line. It is given that f is continuous and differentiable everywhere on the real line. So it is continuous at x is equal to 1 and 2. Here critical points are 1 and 2. F is continuous on the real line, everywhere on the real line means definitely f is continuous at x is equal to 1, 2 and also differentiable, continuous and differentiable at x is equal to 1, 2. So apply that definition of continuity and differentiability at x is equal to 1, 2 so that we can find values of unknowns a, b, c, d. Now first applying a continuity definition at x is equal to 1, given that function is continuous. So at x is equal to 1, function is continuous means that LHL value, there is a before going LHL I can write basic definition. Limit x tends to a, x tends to a means here a value 1, x tends to 1, f of x must be equal to f of 1. Limit x tends to 1, f of x must be equal to f of 1. So again here, when that limit value exists, if and only if LHL is equal to RHL. Left hand limit is equal to right hand limit. Again that left hand limit means here what is that left hand limit? LHL is limit x tends to 1 minus f of x. Left hand limit value. So limit x tends to 1 minus f of x. 1 minus means x value less than 1. When x less than 1, the corresponding function is x square. So the left hand limit value is 1 square, that is equal to 1. Similarly, finding a right hand limit. Right hand limit is RHL. RHL is a limit x tends to 1 plus f of x. X tends to 1 plus means x value greater than 1. When x greater than 1, the corresponding function is ax square plus bx plus c. X square plus bx plus c. Now replacing x with 1, we will get that value a plus b plus c. So given that function is continuous at x is equal to 1, therefore that LHL must be equal to RHL. So it implies, I can write, it implies a plus b plus c is equal to 1. LHL value is 1, RHL value a plus b plus c. So LHL must be is equal to RHL. Then only I can say that limit value exists. So and also what about function value also get the same value f of 1. What is that f of 1 value? F of 1 also 1 will get. For x is equal to 1, function value 1 square is equal to 1. So we get the same equation a plus b plus c is equal to 1. Let it be equation 1. Now applying convoluted definition at x is equal to 2. At x is equal to 2. Again here limit x tends to 2. F of x must be equal to f of 2. So again here that limit value exists if and only if LHL is equal to RHL. What is that LHL here? Limit x tends to 2 minus f of x must be equal to limit x tends to 2 plus f of x. Left hand limit at x is equal to 2 must be equal to right hand limit at x is equal to, then that limit value exists. So again here what is that left hand limit x tends to 2 minus means x value less than 2. When x less than 2, the corresponding function is ax square plus bx plus c. Ax square plus bx plus c. That is equal to limit x tends to 2 plus nothing but x value greater than 2. When x greater than 2, the corresponding function is x plus d. X plus d. So we get replacing x with 2 here, we get 4a plus 2b plus c is equal to here 2 plus d. It implies 4a plus 2b plus c minus d is equal to 2. Minus d is equal to 2. So that is equation 2. That will be equation 2. Now applying differentiability definition. Now given that function f of x is differentiable at x is equal to 1. Applying differentiability definition. What is differentiability? Limit x tends to 1, f of x minus f of 1 by x minus 1 value should exist. When that limit value exists means again here left hand derivative here. Left hand derivative is limit x tends to 1 minus. So when x less than 1, the corresponding function is here x square. X square minus that f of 1. F of 1 is 1. X square minus 1 by x minus 1. So when x less than 1 means corresponding function x square. F of 1 value 1 by x minus 1. So that will give here limit x tends to 1 minus x plus 1 into x minus 1 by x minus 1. So x minus 1 will get cancelled. Replacing x with 1, we have 1 plus 1, 2. The left hand derivative. Now RHD value. RHD is RHD right hand derivative. Limit x tends to 1 plus. So when x greater than 1, we get corresponding function x square plus bx plus c minus f of 1 is 1 by x minus 1. Now here it is given that function is differentiable at x is equal to 1, means LHD must be equal to RHD. So here if you replace x with 1, here in denominator we get 0, so that numerator value should get 0 definitely. Then only we can apply that L'Hopital rule. So here we get a plus b plus c, if replace x with 1 here, a plus b plus c minus 1 by 0. So definitely that numerator value should be 0. So that is applicable for L'Hopital rule. So applying that L'Hopital rule now, the derivative of numerator is 2ax plus b by 1. Now replacing x with 1 we get 2a plus b. So it implies LHD must be equal to RHD. So 2a plus b is equal to 2. So that is equation 3. So now see, we can do this problem in another way also. That is checking differentiability, applying differentiability definition. I can say here R. I can go for another way. Limit. So finding f dash of x directly. What is f dash of x? F dash of x is 2x for x less than or equal to 1. 2ax plus b derivative of c 0 for 1 less than x less than or equal to 2. This is 1 for x greater than 2. For x greater than 2. So here the function f of x is differentiable at x is equal to 1. Differentiable at x is equal to 1. Therefore, we can apply like this. F dash of the right hand derivative is f dash of 1 plus the left hand derivative f dash of 1 minus. So f dash of 1 minus must be equal to f dash of 1 plus. So the left hand derivative equal to right hand derivative. F dash of 1 minus means left hand derivative at x is equal to 1. F dash of 1 plus means right hand derivative at x is equal to 1. So both must be equal. So it implies, see f dash of 1 minus means for x less than 1 the corresponding function is 2x. So replace x with 1, that function will get 2. F dash of 1 plus when x greater than 1 the corresponding function is 2ax plus b. Replacing x with 1 will get 2a plus b. So you get the same equation. Equation 3. We can go for the definition, or directly we can find derivative. After finding derivative, we can apply this condition: left hand derivative is equal to right hand derivative. So now, similarly, we can apply the same thing. This is a shortcut way to apply differentiability. Now, at x is equal to 2, also given function is differentiable. So at x is equal to 2. At x is equal to 2. So what is f dash of 2 minus must be equal to f dash of 2 plus. Since function is differentiable at x is equal to f dash of 2 minus must be equal to f dash of 2 plus. It implies what is f dash of 2 minus means when x less than 2, the corresponding function is 2ax plus b. Replacing x with 2 will get 4a plus b must be equal to f dash of 2 plus right hand derivative. So 2 plus means when x greater than 2, the corresponding function is 1. So 4a plus b is equal to 1. So that is equation 4. Solving all these equations 1, 2, 3, 4, will get finally a value a is equal to minus 1 by 2, b is equal to 3, c value minus 3 by 2, and d is equal to 1 by 2. So these are unknown values a, b stated. Solving these 4 equations. Equation 1, 2, 3, 4. Next question. Let the function of 0, 5 to r divided by this one. The number of points where f is not differentiable in open interval 0, 5. So we need to find number of points where f is not differentiable in open interval 0, 5. So open interval 0, 5 means it contains points 1, 2, 3, 4. It does not include a 0 and 5 because it is open interval. So out of these 1, 2, 3, 4, let us check the differentiability at 1, 2, 3, 4. But here the function is defined between 0 to 1, 1 to 2, 2 to 5. So from this one I can say that the critical points are only 1 and 2. Only 1 and 2. So 3 and 4 are not critical points. So here no need to check differentiability of the given function at 3 and 4. That is not required. The function is always differentiable at all remaining points, except that you have to check only at critical points. So here 1, 2 are all critical points. So we need to check differentiability of that given function at critical points only. At remaining points not required. At remaining points the function is always differentiable. So now checking differentiability at x is equal to 1 and also x is equal to 2. Now see here given function, to check differentiability at x is equal to 1. To check differentiability at x is equal to 1. So we have to check this condition. Limit x tends to 1, f of x minus f of 1 by x minus 1. This value should exist. When this value exists if and only that LHD left hand derivative is equal to right hand derivative. So again here what is the left hand derivative? Limit x tends to 1 minus f of x minus f of 1 by x minus 1 value should be equal to limit x tends to 1 plus f of x minus f of 1 by x minus 1. Let's check this condition. Now see that what is that LHD value? Limit x tends to 1 minus 1 minus, when x less than 1 minus nothing but x less than 1. When x less than 1, the corresponding function is 2x plus 5 minus f of 1. F of 1 means here for x is equal to 1, the corresponding function value is 2 into 1 square plus 5. We get 2 plus 5 7 by x minus 1. So what about this value? Simplify this one, that is equal to, we get limit x tends to 1 minus, we get 2x minus 2 by x minus 1, that is equal to limit x tends to 1 minus, replacing taking 2 common, x minus 1 by x minus 1. So we get 2, left hand limit value 2. And what about the right hand limit value? Checking this right hand limit value. Limit x tends to 1 plus, when x greater than 1 plus means for x greater than 1. When x greater than 1, the corresponding function is 2x square plus 5 minus f of 1 is 7 by x minus 1. So that is equal to limit x tends to 1 plus, we get 2x square minus 2 by x minus 1. X tends to 1 plus, taking 2 common, we get x square minus 1 by x minus 1. So limit x tends to 1 plus 2 into x square minus 1 can be written as x plus 1 into x minus 1. X plus 1 into x minus 1 by x minus 1. So replacing x with 2, by x with 1, we get 1 plus 1 2, 2 into 2 4. So here left hand limit value we got left hand derivative 2, whereas right hand derivative 4, both are not equal. Therefore I can say that given function is not differentiable at x is equal to 1. Given function is not differentiable, you should get same value, both are equal. Then I can say that limit value, that limit of this function exists. Limit of that function exists, I can say that that function f of x is differentiable at x is equal to 1. So we are getting both different values. So the function f of x is not differentiable at x is equal to 1. Now checking differentiability at x is equal to 2 also. See here, we can check this one by using a shortcut method also. We can find directly derivative here, f dash of x. No need to go for this procedure. We can find directly derivative. What is f dash of x value here? F dash of x value is derivative of 2x plus 5 is 2 for 0 less than x less than 1. And derivative of 2x square plus 5 is 4x 1 less than or equal to x less than 2. And derivative of 2 by 3 x cube plus 23 by 3 is 2 by 3 into derivative of x cube is 3x square between 2 to 5. So 3 will get cancelled, 2x square. Now after finding derivative, directly here the LHD is f dash of at x is equal to 1. At x is equal to 1, LHD is f dash of 1 minus. So f dash of 1 minus means when x less than 1, the corresponding function is 2. And RHD is nothing but f dash of 1 plus. F dash of 1 plus, when x is greater than 1, the corresponding function is 4x. Replace x with 1, we get 4. So we get LHD 2, RHD 4. LHD not equal to RHD, therefore given function is not differentiable at x is equal to 2. So this is the shortcut method to check differentiability. Or we can go for that definition also. Now similarly checking differentiability at x is equal to 2 also, using the same shortcut method. So at x is equal to 2, what is the LHD left hand derivative f dash of 2 minus, I can say that. LHD is f dash of 2 minus. When x less than 2, the corresponding function is 4x. Replace x with 2, we get 4 into 2h. RHD f dash of 2 plus, when x greater than 2, the corresponding function is 2x square. Replacing x with 2 square, 4 into 2, 8. So at x is equal to 2, we got LHD 8, RHD also 8. Both are equal, therefore I can say that the function is differentiable at x is equal to 2. But whereas the function is not differentiable at x is equal to 1. So the number of points where f is not differentiable in the interval open interval 0, 5 is only 1. At x is equal to 1 only it is not differentiable. At x is equal to 2 differentiable. What about 3 and 4? 3 and 4 are not critical points. So no need to check at 3 and 4. The given function is always differentiable at 3 and 4. So the final answer is 1.